All right, let's take a deep dive into thermal physics today. Specifically, we're looking at the core concepts from the AQA A-Level syllabus.
Think of this as your physics crash course, ready to help you smash that exam.
Perfect. Let's start with something I always find a little tricky, internal energy.
Yeah.
What exactly is internal energy?
Okay, so imagine it like this. Internal energy is the total energy stash of a substance. It's all the kinetic energy, from the particles zipping around, plus the potential energy locked away in the bonds between them.
So it's like all those tiny particles are having a party, and the internal energy is like a measure of how wild the party is.
Yeah, exactly. The more they're moving and grooving, the stronger the forces holding them together, the higher that internal energy is going to be. Now think about what happens when you heat a pan of water.
The water molecules, they start moving faster, right?
Right. They're gaining kinetic energy, bouncing around like crazy. And as they do that, what happens to the water's temperature?
It rises.
Exactly. But here's where things get really interesting. What happens when that water starts to boil?
Well, the temperature stays at 100 degrees Celsius, even though we're still pumping in heat.
That's the key. That energy you're adding isn't making the molecules move any faster at that point. It's breaking the bonds between them, letting them shift from liquid to gas. And we call that energy latent heat.
So it's like the energy is being used to, I don't know, promote those water molecules, get them to a higher energy level as they go from liquid to gas. It's not just making them dance faster.
Absolutely. A great way to put it. Temperature stays put during a change of state because that energy is busy rearranging things, not speeding them up.
That makes a lot of sense. So how do we actually calculate those energy changes happening in a substance?
Well, there are two main formulas to keep in mind. First, for changes in temperature, we have Q met delta. Here, Q is the heat energy transferred, M is the mass of your substance, C is the specific heat capacity, which tells you how much energy a substance can store, and the is the change in temperature.
So specific heat capacity that tells us how much energy we need to heat up a certain amount of something by a certain temperature, right?
Right.
Like water. Water's got a high specific heat capacity. It takes ages to heat up.
Exactly. And that's why water is such a good heat sink. Think about radiators or hot water bottles. Now, for changes in state, we use a different formula, Q equals mL, where Q is still heat energy, M is still mass, and L is the specific latent heat.
I remember learning about two types of latent heat, fusion and vaporization.
Exactly. Fusion is all about melting a solid or freezing a liquid, and vaporization is for boiling a liquid or condensing a gas.
So if we know the mass of a substance and its specific latent heat, we can figure out how much energy we need to change its state. Could we try an example?
Sure. Imagine we have 100 grams of ice sitting at 0 degrees Celsius. To melt it all, we'd use our QLA formula. Mass M would be 0.1 kilograms, that's 100 grams converted, and L is 334,000 J kilograms, which is the specific latent heat of fusion for ice.
So Q, 0.1 kilogram, 334,000 J kilograms, which gives us 33,400 joules.
You got it. That's the energy needed to melt that ice without changing its temperature.
Okay, so we can use these formulas to figure out energy changes for heating, cooling, melting, boiling, the whole shebang.
Yeah.
It's all starting to click now.
Excellent. Now, let's switch gears a bit and talk about gases. How do we think about energy and temperature when we're dealing with these things?
Gases always seem a bit more, I don't know, unpredictable because their volume changes with temperature and pressure.
You're right. Gases have that freedom to expand and contract, which makes them really fascinating to study. And their behavior is governed by three main laws: Boyle's law, Charles's law, and the pressure law.
Right, let's start with Boyle's law. That's the one about pressure and volume. Right?
Exactly. Boyle's law tells us that at a constant temperature, the pressure of a gas is inversely proportional to its volume. Basically, squeeze a gas into a smaller space, its pressure goes up.
Like squeezing a balloon. The harder you squeeze, the higher the pressure inside.
Exactly. Now, what about Charles's law?
That one's about volume and temperature, right?
You got it. Charles's law states that at a constant pressure, the volume of a gas is directly proportional to its absolute temperature.
Wait, absolute temperature, you mean on the Kelvin scale?
Precisely. The Kelvin scale starts at absolute zero, -273.15 degrees Celsius, which is 0 Kelvin. At absolute zero, particles have zero kinetic energy, no movement at all.
So Charles's law is saying that if you heat a gas, but keep the pressure the same, it expands and takes up more space.
Exactly. Imagine a hot air balloon. As the air inside is heated, it expands and becomes less dense, making the balloon rise.
Makes sense.
Yeah.
And lastly, we have the pressure law that links pressure and temperature, right?
Right. At a constant volume, a gas's pressure is directly proportional to its absolute temperature. So heat up a gas in a sealed container, the pressure inside will increase.
Got it. So these gas laws give us a way to predict how a gas is going to behave under different conditions. Is there a way to combine all these laws into one big equation?
There is. It's called the ideal gas equation. PV equals nRT. Here, P is pressure, V is volume, N is the number of moles, R is the ideal gas constant, and T is the absolute temperature in Kelvin.
So many variables in one equation. But it's basically telling us how pressure, volume, temperature, and the amount of gas all relate to each other.
Exactly. The ideal gas equation is like our master key for unlocking all sorts of gas problems. For instance, you can calculate the pressure of a gas if you know its volume, temperature, and the amount of gas you've got.
It's a pretty handy tool to have then. But how did we even come up with this ideal gas equation? Is it based on some understanding of how gas molecules are actually behaving?
That's a great question. You see, those gas laws, they're empirical, meaning they came from observations and experiments. But to truly understand why gases act the way they do, we need to go deeper into the kinetic theory of gases.
Oh, right, the kinetic theory? I've heard of it, but I'm not sure I really understand it.
Okay, so picture this. Gases are made up of these tiny particles, atoms or molecules, and they're constantly zipping around in every direction. Their motion, their kinetic energy, that's what determines the big picture properties of the gas, like pressure, volume, and temperature.
So it's like a microscopic dance party, and the way they're moving determines how the gas behaves as a whole.
Exactly. The kinetic theory of gases is a model. It explains the behavior of gases based on the motion of all these little particles. And it starts with a few key assumptions.
What kind of assumptions?
Well, first, it assumes that those gas particles are in constant random motion, bouncing off each other in the walls of their container.
Like a never-ending game of microscopic bumper cars.
Precisely. Second assumption is that those collisions are perfectly elastic, meaning no energy is lost during the collision. Think of it like those super bouncy balls. They just keep bouncing back with the same energy.
Right, if they weren't elastic, the gas particles would eventually just slow down and lose energy. What else?
Third assumption. The volume of the particles themselves is negligible compared to the volume of the container. So we're mainly focused on the space between the particles, not their actual size.
So it's like we're picturing the gas as mostly empty space with these tiny particles whizzing around?
Exactly. Fourth assumption, there are no forces of attraction or repulsion between those particles. They only interact through those elastic collisions.
So they're like independent entities, not really bothered about each other in this model.
Right. And finally, the average kinetic energy of the gas particles is directly proportional to the absolute temperature of the gas.
Meaning, the hotter the gas, the faster those particles are moving, on average.
You got it. That's the crucial link between that microscopic world of those tiny particles and the big picture properties of the gas that we observe.
Wow, that is fascinating. So, by understanding how these tiny particles are behaving, we can actually explain why gases behave the way they do.
Exactly. The kinetic theory is really powerful for understanding the world of gases.
Incredible. We've peeked into the hidden world of gas molecules and seen how their frantic dance determines those properties of the gas as a whole.
And we've just scratched the surface of thermal physics. There's so much more to uncover.
So we've been talking about ideal gases, but I'm guessing real gases don't always behave quite so perfectly, right?
That's a sharp observation. You're right. The ideal gas model is great for lots of situations, but real gases, they can be a bit trickier, especially when you're dealing with high pressures or low temperatures.
Why is that? What's going on at the molecular level to make them act up?
Remember those assumptions we made in the kinetic theory? Well, in reality, gas particles do actually take up a small amount of space, and sometimes there can be these tiny forces of attraction between them.
Right, we were pretending they were like those perfectly bouncy balls with no size and no attraction to each other.
Exactly. So when you crank up the pressure, that space between particles gets squeezed, and suddenly the volume they take up starts to matter.
Like cramming too many people into a tiny room, they start bumping into each other more.
Exactly. The assumption that the particle's volume is negligible, it kind of breaks down. And then when the temperature drops really low, those weak intermolecular forces, they become more noticeable because everything is moving slower.
So instead of just bouncing off each other, they might start sticking together a bit.
Exactly. And all these things can make real gases deviate from what the ideal gas law predicts. But don't worry, for most everyday situations, that ideal gas model, it still works pretty well.
Good to know. It's a good reminder that models are just that. Models, they simplify things, and sometimes we need to remember the details we've left out.
Absolutely. Now let's put what we know about gases to the test. Ready for a practice problem?
Hit me with it. I'm feeling up for a challenge.
Okay, here we go. We have a container, volume of 2 cubic meters, filled with 10 moles of nitrogen gas, sitting at 300 Kelvin. What's the pressure inside that container? We'll assume it's acting like an ideal gas.
Okay, so we can use our handy ideal gas equation, PV equals nRT. We know the volume V, number of moles N, and the temperature T. We need to find P, the pressure. What about R, the ideal gas constant?
That's a fixed value, 8.31 joules per mole per Kelvin. So we've got all the pieces we need to plug in and solve for P.
Right, let's rearrange that equation to solve for P. So that gives us P equals nRTV.
Perfect. Plug in those numbers and see what you get.
Okay, plugging them in, we get P 10 mole, 8.31 Jmol K, 300 K, 2 meter 3. So crunching the numbers, I get a pressure of about 12,465 pascals.
You nailed it.
I'm feeling pretty confident about those gas law calculations now. But I'm curious, we've talked about heat transfer as this one-way energy moves around. Are there other ways energy can be transferred?
That's a great question. There are actually 3 main ways energy gets transferred: conduction, convection, and radiation.
Okay, let's break this down. Starting with conduction, what's that all about?
Conduction is heat transfer through direct contact. Imagine touching a hot stove.
Ouch. Heat flows from the stove to my hand and I get burned.
Exactly. What's happening at a microscopic level is that faster moving molecules in that hot stove are bumping into the slower ones in your hand, transferring some of their kinetic energy.
So it's like this chain reaction of collisions passing the energy along.
A great way to picture it. And different materials conduct heat differently. Metals, they're excellent conductors. They've got free electrons that can easily pass that energy along.
Right, that's why a metal spoon heats up so quickly if you leave it in a hot pot. What about insulators then?
Insulators, things like wood or plastic, they're poor conductors. Their molecules aren't as tightly packed, and they don't have those free electrons to move the energy around.
So that's why you can stir a hot pot with a wooden spoon and it stays relatively cool.
Okay, so what about convection? How's that different?
Convection is all about the movement of fluids, liquids or gases. They transfer heat as they move.
So it's not just molecules bumping into each other. The whole fluid is moving and carrying that heat energy with it. Exactly. Think of a pot of boiling water. The water at the bottom heats up, becomes less dense, and starts rising, while the cooler water at the top sinks. You get this circular flow, a convection current.
It's like a natural circulation system driven by heat. That explains why the water gets all mixed up, not just hot at the bottom.
Precisely. Convection is behind so many things: weather patterns, ocean currents, even the movement of magma inside the Earth.
Wow, it's everywhere. Okay, last one, radiation. How does that work?
Radiation, that's heat transfer through electromagnetic waves, like light or infrared radiation. It doesn't need anything to travel through. Unlike conduction and convection, it can travel through the vacuum of space.
So that's how we get heat from the sun, even though there's no air between us and the sun.
Exactly. The sun emits all sorts of electromagnetic radiation, including infrared, which we feel as heat. When it reaches Earth, the surface absorbs it and we warm up.
So just to recap, conduction is direct contact, convection is about fluids moving, and radiation travels through space as waves. 3 totally different ways for heat to move around.
Great summary. Now, before we wrap up this part, I have a question for you. We've been talking about average kinetic energy of gas molecules being related to temperature, but do you think all the molecules in a gas are moving at the same speed?
That's a good one. I have a feeling they're probably not all moving at the same speed.
You're right. In any gas at a specific temperature, the molecules actually have a whole range of kinetic energies. Some are zipping around, some are taking it easy, and there's everything in between. To really understand how those speeds are spread out, we need to talk about something called the Maxwell-Boltzmann distribution. That's a topic for our last part, though.
All right, let's tackle this Maxwell-Boltzmann distribution, and it sounds a bit complicated.
Don't worry, it's not too bad once you wrap your head around it.
Yeah.
Imagine a racetrack, right, with all these cars. And they're all going in the same direction, but some are speeding ahead, some are just cruising, some are lagging behind.
So it's like a molecular racetrack, with those molecules zipping around at all these different speeds.
You got it. The Maxwell-Boltzmann distribution is like a snapshot of that racetrack. It shows us how many molecules are moving at each specific speed.
So instead of just having that average speed, We get a more detailed picture of the whole spread of those molecular speeds.
Exactly. And the really cool thing is that we can picture this distribution as a bell-shaped curve.
A bell curve, like the ones you see in statistics.
That's the one. The peak of that curve, that's the most probable speed. The speed that most of those molecules are moving at. It's like the most crowded part of our molecular racetrack.
So it's not the average speed, it's the most common speed among all those molecules.
Exactly. And as you move away from that peak, the number of molecules moving at those speeds dropped off. So there are fewer molecules at the very high speeds and the very low speeds.
So most of them are clustered around that most probable speed, but there's a whole range of speeds on either side.
Now here's where things get even more interesting. The shape of this curve actually changes with temperature.
So it's not just a static picture, the whole distribution shifts as we heat or cool the gas.
Right. As the temperature climbs, the whole curve shifts to the right.
Meaning the most probable speed goes up, and more molecules are moving at higher speeds overall.
You got it. It's like we're heating up that racetrack, all the cars get an energy boost and speed up. And not only does that peak shift, the whole curve gets wider too.
So the range of speeds gets broader at higher temperatures.
Exactly. At higher temperatures, you get a bigger spread of molecular speeds, from the real speed demons to those that are taking it easy.
Okay, I think I'm getting it now. So the Maxwell-Boltzmann distribution tells us how those speeds are spread out in a gas at a particular temperature.
Precisely. And it's a really useful tool for understanding all sorts of things in chemistry and physics.
Like what, for example?
Well, think about chemical reactions. For a reaction to happen, those molecules need to collide with enough energy.
Right, enough to break those bonds and form new ones.
Exactly. The Maxwell-Boltzmann distribution tells us what fraction of those molecules have enough energy to react at a given temperature, so we can understand how temperature impacts reaction rates.
That's fascinating. This distribution, it has real-world applications.
Absolutely. It helps us understand things like diffusion, too. You know, how molecules spread out from areas of high concentration to low concentration.
Like how the smell of baking cookies, it spreads from the kitchen to the rest of the house.
Exactly. The faster those molecules are moving, the faster they can spread out. And the Maxwell-Boltzmann distribution gives us that insight into those molecular speeds.
This has been incredible. It feels like we've zoomed right into the microscopic world of those gas molecules and seen how their individual speeds actually affect the properties of the gas as a whole.
That's the beauty of physics, connecting the microscopic world to the macroscopic world.
Well, this deep dive into thermal physics has been absolutely mind-blowing.
I'm glad to hear that. We've covered a lot of ground, from internal energy and gas laws to the intricacies of the Maxwell-Boltzmann distribution.
It's been a wild ride, but I feel like I've come away with a much deeper understanding of how heat, temperature, and the behavior of matter are all linked together.
And remember, this is really just the beginning. There's always more to explore in the fascinating world of physics.
So keep those physics brains engaged, keep asking those curious questions, and we'll see you on our next deep dive.